Huh. That's funny. Oh, okay. So, oh, I get it. So if we do x dy minus y dx, because it's the identity map, it's equal to its own pullback. But that's interesting, because if we use the polar coordinates, we'll get something different. See, so like, so what do we got? We've got, you know, x is, I don't like id for this. I mean, I'd prefer to, I don't know, guys, like, it's wrong. It's not wrong, but it's just bugging me. Anyway, let me get to the point here. If you want to make this a different letter, like F, put black under F, all of a sudden it would feel less illegitimate to me personally, but anyway, so the bottom line is you're plugging in for x what it's equal to in terms of the original. So that gives you r cosine theta, and then we've got the differential of r sine theta minus r, oh, that's supposed to be a y, wasn't it? Yeah. Yeah, my bad. You guys got it. So minus r sine theta, the differential of r cosine theta, which is equal to r cosine theta times r cosine theta d theta minus, or rather plus sine theta dr minus r sine theta times cosine theta dr minus r sine theta d theta. Right? But you notice that the dr terms, they be canceling because you got cosine sine and sine cosine, but off by a minus, so and then you got cosine squared and you got sine squared, so lo and behold, you get yourself a r squared d theta. But the pullback is a contravariant functor, so like one of the things about being a contravariant functor is the pullback of the identity is just the identity on the space. So like that's why these are equal. We literally can derive from this that d theta is equal to x dy minus y dx divided by r squared, which I'll write as x squared plus y squared. There you go. That's one of my favorite things to integrate in Calculus 3, right? Because if you integrate this around a circle, right? Let's say, you know, S1, well, that's this thing. But of course, this is obviously 2 pi, right? So the integral of this particular covector field around the circle gives us 2 pi. This is an important example, very important example in the story of integration. So next up, he talks about restricting covector fields to submanifolds. All right? And so there the story is even simpler than it was for, like, if we talk about we have a vector field to a manifold, we could talk about, is it a tangent vector field to a submanifold? So in order for that to actually have been reasonable, we needed that that tangent vector field actually, that vector field actually was tangent to the submanifold, right? Which it wouldn't necessarily be, because part of the vector field could be pointing off the directions of the submanifold. On the other hand, here, if you have a covector field on the manifold and you want to, you know, find a corresponding covector field on the submanifold of the manifold, you literally just restrict it, So the pullback under the inclusion map amounts to simply restricting the covector field on the manifold to whatever defines the submanifold. And but beware, as he points out, that if you pull back a covector field on a manifold which is non-zero, you may nevertheless get a zero covector field on your submanifold. For instance, I guess I can fit it in here. Like if you're, maybe your omega is like dy. I think this is the example he gives. So, here's the manifolds R2, right? And so there's two sort of stupid submanifolds to think about here, right? Like you could think about this one, what's this? The y-axis. You can think about the x-axis, right? Those are one-dimensional submanifolds of R2. And what's the equation of this one? The equation of the y-axis is x equals to 0, right? The equation of the x-axis is y equals to 0. So if we talk about, let me call this, I don't have a good name for it. What do you want to call the point set of the x-axis? I guess we could call it the flat line. So this is m, all right? So like s, let's call it s x-axis. Sx is equal to, like r Cartesian product 0, right? Whereas sy would be 0 Cartesian product with r, right? Can I erase my black stuff here? Thank you. So, what's the deal with my differential there? Like, how does that pull back? So if I talk about the iota map of the x-axis being included into R2, right? Then what's the pullback under the inclusion map of omega? And let me call that iota x. Whereas what would be the iota y pullback of omega?
Circle, push forward to R2 and then take it back.
I guess iota y of y is 0y, right? Iota x of x is x0. So if I do the pullback of omega under, what's the pullback of dy? What's the pullback of dy here? So I think I'm supposed to do the differential of what? Of iota x of what? No, it's y, right? It's y composed with iota x. Wasn't that it? Isn't that what the proposition had? Yeah. So what is that, though? We're viewing y as the coordinate map, right? So like y of, so when you look at y of, this is asking what's the second component. In each case, this is asking what's the second component function of the inclusion map. So inclusion map, second component function is y. So the second one is literally dy. This one is d of 0. I'm sorry. Yeah, this one. So see that 0? That's that 0. This 0 is this 0. So, and the different, of course, this is 0, right? So my point to you is that dy is a non-zero covector field on the plane, but it pulls back to 0 on the x-axis, because the x-axis is where y is equal to 0. So of course dy is equal to 0 on the x-axis. So there's two different ways to understand what I just said, which is one is just to literally plug y equals 0 into dy, and the other is to go through this formal pullback method. But they yield the same thing. The pullback formalism is a technology to make rigorous this notion of substitution. And it's pretty awesome. Let's see here. So there's that. That brings us to the last 10 pages of this chapter, which are Calculus 3. You have to leave. You have to be somewhere at 6. I have to vote at 6, so we have that in common.
But mine's away from
No, I vote like wherever I vote. But we'll probably be done in about 15 minutes. Is that okay? Okay. So I will not prove anything. I'll just talk. I will tell you, though, that the proofs in this book, in the last 10 pages, give you perhaps some of the most elegant forms possible for the proofs of the theorems of line integrals in vector calculus. The last 10 pages of chapter, I'm talking about page 287 to 298. So these 10 pages are on line integrals. And so let me just tell you like what happens. And I'll tell you, you should read it. I mean, we don't have time to do everything in class. Some of these proofs I really love. But I do these proofs in Calc 3, but not in as elegant a way as he does here. So the first thing is he defines how we can integrate a covector field. What's the integral of a covector field? The integral of a covector field along a curve, well, he first defines the integral of a covector field along the real line to be this. Integral from a to b of f of t dt, basically. So this would be like for omega equals to f of t dt. This would be a covector field on, let's say, the closed interval from a to b, if you like. Or you could say on the reals. And then he proves that this notion of integration is invariant with respect to reparameterization. He calls it the diffeomorphism invariance of the integral. He proves that, among other things, that like if you have the integral of a increasing so if you pull back under omega and integrate over c comma d, that's the same as if you just integrate over omega of a comma b. Here, phi is a mapping that goes from a comma b to c comma d. Maybe the other way around. Yeah, the other way around. Pull back, yeah. So that's one thing. If you have a strictly increasing map like that, then this is equal. If you had a strictly decreasing map, it gives you a minus. This proposition 11.33, I won't prove for you guys today, but I mentioned it last time. It's a really interesting, beautiful proof, but it's kind of like what we already did today. If M is connected smooth manifold with or without boundary, any 2 points of M can be joined by a piecewise smooth curve segment. He builds a set C that's Q in the manifold such that there exists a piecewise smooth curve segment from P to Q. He then argues that this set C is both open and closed. Since it's connected, it's everything. And I read through this proof earlier today. It's actually quite understandable. If you just spend like 5 minutes reading it, it'll make sense to you. Basically, it's just exploiting the coordinate ball and the fact that the coordinate ball gives you a diffeomorphism to Rn, where you can easily connect points inside balls down there. So, as usual, it's thievery. He then proves that if you have a smooth curve from A to B to a manifold, right, then we can talk about the line integral of a covector field along this line to be simply the integral from A to B of the pullback under the path of omega. And he talks about the properties of this integral. This integral is additive. You can pull constants out. If it's a constant map, it integrates to 0. Wonderful properties. With respect to this definition, he integrates the curve, the differential form d theta, and gets 2 pi. All right. It turns out that if you had a different reparameter, so like this, if we think about the manifold, then this would be gamma of AB. It's a specific set of points. We could call that set of points C. And in some sense, it makes sense to say that this is really the integral over C of omega, in the sense that this would actually be equal to the integral over, let's say, phi star of omega over CD, if phi went from CD to M, and this was another parameterization of the same curve.
Different C.
Oh, bar. There we go. Bar. Great. And so specifically, this is how you do it. Integrate over gamma. Actually, the way that works is integral from A to B of omega at gamma of t, right, times gamma prime of t dt. All right? And from this, he proves the fundamental theorem of calculus for line integrals. Fundamental theorem of calculus for line integrals. He gets that the integral over a curve of df is just equal to f of gamma of b minus f of gamma of a. All right? And technically speaking, if gamma is only assumed to be piecewise linear, so you do the integral over each piece of the line and you add it together, the interior points cancel out, and that's what you get. Then he gives us a definition. Omega is exact if and only if omega is equal to the differential of some function. So to exactness is the equality of, you're able to build the covector field. You're able to build the covector field from the differential of the function. And he has this omega is conservative. Is conservative if and only if the integral around loops of omega is equal to 0. And he calls it a closed curve segment. And then he gives his proposition, A as proposition, which says that the integral along gamma 1 of omega is equal to the integral along gamma 2 of omega if and only if omega conservative if and only if omega exact. And here, to be clear, these are coterminal paths. Same starting and ending points, coterminal paths. So here he's talking about the equivalence between the existence of a potential function, the integral around loops being 0, and the path independence. You should recognize this from the discussion in Calculus 3 of conservative vector fields. Do you see why this is just a line integral in disguise? Contrast this to like the integral from, say, a to b of a vector field f of r of t. This is not in John Lee's book, dotted with dr dt. dt. That's the definition of line integral from Calculus 3. Notice that this right here, omega of gamma of t, if we rewrite that, it's like partial, let's say gamma I, partial xi, my bad, I'll get it eventually here. D gamma I dt, partial xi. So that is literally just, when you write it out, omega I at the point times d gamma I dt. But it is literally this same thing. If you can see through it. The proof on page 293 is just beautiful. He shows explicitly, like, it's not easy to get from the path independence to the exactness, but he actually shows you how you can build a formula for f by using the path independence. It's explicitly given there. And I really will shut up soon here. And then, more importantly, he introduces the concept of a closed omega. This means that for him in this chapter, it means that partial of omega I, partial xj, is equal to partial omega j, partial xi. So you might recognize this as the closed condition from differential equations, like partial y of m is equal to partial x of n. Or you might recognize it as the curl condition from Calculus 3, like the curl of a vector field being 0. What that means is that the mixed partial derivatives of components of the vector field with respect to the variables which are not present have to be matching. Like, for instance, this thing right here is actually a closed vector field. Closed form, rather. The d theta is closed, as it turns out. And proposition exact implies closed. That's easy to prove. The reason that that's easy to prove is exact gives you that the components, so like this basically tells you that omega I is partial f, partial xi, right? And so commuting of this equation here just amounts to commuting partials. See, because the ith component of omega for an exact one is the partial derivative. When you take a partial derivative of that, you get a mixed partial, and they commute for a smooth function. The interesting thing, the very interesting thing, is that the converse direction is not generally true. And in fact, it's how we detect topology of spaces. That is a closed form. The d theta is a closed form, which is not exact. And the reason for that is because you're missing the origin. The existence of a form which is closed but not exact is a signature that your space has topology. This is the origin of the de Rham cohomology, which was born in part from looking for potentials for physical functions. And then there's proposition 11.45. Anyway, I will resist the urge to lecture on the rest of this chapter and let you guys read it. It is really, really neat. But truthfully told, it's all calculus 3 just done on a manifold. It's very cool. Don't worry, I'm not teaching calculus 3, they're safe.